We're constantly told that data is the new oil, and that machine learning thrives on massive amounts of information. But does feeding a computer every single piece of data we can find actually make it smarter, or can it sometimes make it dumber? Let's say we want to build an algorithm that can accurately predict the final sale price of a house. To do this, we give the model context. We start with basics, mapping out inputs like the number of bedrooms and bathrooms. But what if we also know the size of the television inside the living room? Should we include that too? The instinctive approach in the era of big data is to throw all of it in. We assume the machine will parse through the pile and figure out what matters on its own. Before our algorithm can evaluate a property, we have to translate that physical structure into a mathematical format the computer can actually read. In data science, we organize this information into a table. Every row represents a unique house. Every column is a feature, like the bedroom count or TV size. Finally, we define our goal. That last column is our target, the dollar amount we want to predict. Now we face a problem. If we feed our model irrelevant features like television dimensions right alongside the structural footprint of the house, will the algorithm just ignore the useless information, or will that extra data actively confuse it? To find out, we can test this inside a Python Jupyter notebook, which is the standard environment engineers use to build and test their models. Here is our raw dataset loaded into the code. We have our standard structural features, and right next to them, our highly suspicious television variable. Before we pass any of these numbers to an algorithm, we need to map out how each individual feature relates to the final house price. These scatter plots show how our features behave. On the right, bedrooms against price shows a clear upward trend. More bedrooms generally mean a higher price, but look at TV size on the left. The dots are scattered randomly across the board. A 75-inch screen doesn't drive up the property value, and a tiny screen doesn't lower it. This column might add data to our spreadsheet, but statistically, it only acts as noise, drowning out the true signal. This brings us to a crucial step in preparing data, the deliberate process of identifying and removing that irrelevant information, known as feature selection. Inside our code, we write a single command to drop the TV size column entirely. Our table shrinks, leaving only the variables that actually influence the housing market. With a clean dataset, we perform one final prep step. We separate our data into two distinct groups. The selected inputs, our bedrooms and bathrooms, become our features, or X. The price we want to calculate becomes our target, or Y. By explicitly deleting data, we haven't lost anything valuable. We've actually given the algorithm a much clearer path, forcing it to focus strictly on the numbers that drive real-world outcomes. Now we can finally feed this distilled dataset into our machine learning model to generate a prediction. The result is immediate. When we ran this model with all the raw data included, its accuracy stalled at 78%. But after performing feature selection, that accuracy jumps to 83%, giving us a highly confident final price prediction. If we had left the television sizes in the dataset, the model might have tried to invent a mathematical relationship that didn't actually exist. In data science, this is known as overfitting, when an algorithm memorizes chaotic noise instead of learning the foundational patterns. Chopping out that noise has cascading benefits. The model runs faster, needs far less computing power, and is much easier to audit. Building a highly accurate predictive system isn't about hoarding the maximum amount of raw information you can find. It requires actively curating the highest quality inputs. Sometimes, making a model smarter requires giving it less data